Okay, guys. Welcome to fourth quarter. Yay! Yeah, a few more weeks without spring break. Then you'll forget everything you learned. And then a few more weeks after that, you'll have your semester exams. It'll be summertime. And you'll go have fun and goof around. And some teachers will go to workshops. Some teachers will go to Hawaii. But I have up here some water.
What's that?
Water. I've made it green so you could see it a little bit better. It's warm, but it's not boiling. But it's warm. My question for you is this. If I take this water and I pour it on the table, like that, is it going to be here tomorrow?
Probably not.
No. Why?
Evaporation.
It's going to evaporate. You know that it's going to evaporate. And one of the things that we learned early on, and hopefully we remembered, is that the temperature that water boils is how warm? 100 degrees Celsius. 100 degrees Celsius. And if you're a Yankee, that's 212 Fahrenheit. So that's really warm. 100 degrees Celsius is painful. If you need any proof, next time you make mac and cheese, just plunge your hand in the boiling water. That's what it feels like. So you told me that this water is going to evaporate, which means it's at 100 degrees. No. Ow! Wait, it's not. It's not 100 degrees. Neither is this. Like, ow! This is warm, but it's not hot. I can leave my finger in it for a bit. So why does it evaporate? In any sample of water. Wow. In any sample of water, or any sample of anything, there are some molecules that are warm enough to evaporate. There are some molecules that are cool enough to freeze. And there's freezing and melting happening at the same time. And there's evaporation and condensation happening at the same time. And it is those processes that we're looking at this unit. We're going to be studying equilibrium of state, physical equilibrium. We're going to look at how a solid becomes a gas becomes a solid becomes a liquid becomes a solid becomes a gas becomes a liquid. Now, before we move on any further, there's something we need to discuss. In a compound, at the molecular level, everything's moving. Okay? The kinetic molecular theory tells us that there's that even solids, all particles are in random and constant motion. Gavin, do you want to switch places with Michael?
I'm good.
Because that can happen. All right, so liquids, it should make sense. So liquids are moving, gases are moving, they're moving a lot faster, but even solids are moving. So even the solids that make up your table are moving. They're just not moving very much. You are emulating a solid. You are fixed in position. You move around a little bit. I can see most of you are moving around. Some of you are just like almost completely passed out, not moving very much, but you're all moving a little bit. But you're fixed in position. So you're emulating a solid. In compounds, there is a constant battle between the rules that make compounds want to not move. Those are intermolecular forces. You are fixed in your seats. Why? Why are you in this room sitting in chairs?
Because I'm forced to every day.
Because you're forced to. Because that's the rules. Okay? The rules say you sit down and you listen to an adult blab at you for 40 minutes. Okay? That's the rules. So you're fixed in position because of the rules. If the rules were not there, that said you didn't need to come to school and sit in chairs, what would you be doing?
Not playing Red Dead.
Yeah, you'd be playing video games. You'd be out on your skateboard or your rollerblades, or you'd be walking around. You'd be walking your dog. You'd be out in life, right?
Yeah.
Well, molecules do the same thing. There is a constant battle in the molecular realm, guys, between the kinetic energy and the intermolecular forces. Pretend you can actually see my red pen. This red pen is about done. Let's go. Kinetic energy and intermolecular forces. There's a constant battle between the intermolecular forces that want the molecules to come together and the kinetic energy that want the molecules to fly apart. Does this idea make sense?
Yes.
Because that's going to be the basis for everything we're doing this week in physical equilibrium. Okay, so here we are. So this is our distribution. We talked about this before. So the water that's hanging out on the table, there's a few molecules that are warm enough to boil off. There's also a few molecules that are warm enough to freeze, or cold enough to freeze. They're going to freeze and then rethaw, remelt. Some of the molecules are going to evaporate. If they're close enough to the surface, they'll evaporate and leave. If they're not close enough to the surface, they'll evaporate and then recondense when they bump into something else. So this is a temperature distribution. Distribution is just a fancy way of saying average. Okay? So when we learn temperature, we learned that temperature is an average of the kinetic energies, right? So we learned that temperature is the average kinetic energies of particles. So how do you make it boil where the bubbles are big enough to form together and come to the rise to the top? How do you do that? Exactly. To make something boil, you just take this distribution and you drive it over till there's so much of the distribution over here that bubbles form and they're big enough to rise to the top. That's boiling. Where there's so many over here that the bubbles form and rise to the top. Okay. Make sense? So give me a thumbs up if you're okay with this concept. Okay. So all but one of you in this room have seen this before. We've talked about this before. But I just want to make sure that you all understand this stuff. It's crazy stuff. Shall we move on? Let's move on. Okay, so solids. Behavior of solids. What can you tell me about solids? Give me a property of solids.
They're dense.
They stay in shape. They're very dense. Yeah, they stay in shape. They're very dense. And why do they stay in shape? Why are they very dense?
Because the forces are strong.
Exactly. Okay. So particles are very close together and they're fixed in position. Why are they close together and why are they fixed in position? Because they have very low kinetic energy and very high intermolecular forces. So the hallmark of a solid is the intermolecular forces are very strong, the rules are very strong to hold them together, and the amount of energy they possess that want to fight with the rules is very low. I mentioned this at some point in the past. I think we were talking about gases. That a cubic centimeter of a solid, like if this was ice, a cubic centimeter of ice would fill up 1 liter if it was turned to a gas. If you had a tiny piece of dry ice about yay big, it would make enough gas to fill up the liter. A liter is 10 centimeters by 10 centimeters by 10 centimeters. A cubic centimeter would basically make 1,000 cubic centimeters. Which is why when you put little slivers of dry ice in your 2-liter bottle and you cap it off, when that dry ice sublimates into a gas, it wants to occupy 1,000 times its volume. So if you had a 2-liter bottle, you would only need 2 milliliters of dry ice to fill it up. 2 of those. That's all you need. Yeah. If there's too much, it goes kaboom. So density of solids is about 1,000 times that of gases. 1 milliliter will turn into a liter, about. Make sense so far? So that's solids. So in solids, if the intermolecular forces are winning, raise your hand. You think the intermolecular forces are winning? Yep, that's what's going on. Okay. Now, if you heat it up, you heat up a solid, let's just use ice because it's easy. You heat it up and heat it up. By increasing the temperature, what are you increasing? The kinetic energy. And you increase the kinetic energy eventually, and that solid will turn into a liquid. Now, with a liquid, the molecules are still pretty close together, but they're no longer fixed in place. This is your art class, or your drama class, where the rules, or your PE class, where the rules are a little less strong. Okay? It would be very strange if you walked around the room constantly in an English class, or a science class, except in Latin, or a math class. But in PE, that's what you do. The rules just aren't, they're not as strong. Similarly, in a liquid, the rules are not as strong, the intermolecular forces are not as strong, and your kinetic energy is a little bit higher. Yes?
Aren't it like almost very similar? It's like energy forces are kind of similar, right?
For each compound, every compound, that relationship is unique.
Yeah.
So you can't say when they are equal, you just say that they're higher. The intermolecular forces are lower in a liquid than a solid, and the kinetic energy is higher in a liquid than a solid.
So it's all relative.
Yeah, it's all relative. Okay? Now, liquids have some interesting properties, and they have a little bit of Latin in here too. Latin you should know anyway. Latin is fun. Cohesion literally means glued together. So, liquids have cohesive forces. They have cohesion. This cohesion creates surface tension. Cohesion is the sticking together of similar molecules. Water molecule for water molecule. We talked about this stuff way back in November when we talked about intermolecular forces, the hydrogen bonding, and the van der Waals forces, how molecules want to stick together. Well, this is what it creates. It creates cohesive forces. Water molecules want to stick to water molecules. This is why it hurts when you do a belly flop into the swimming pool. This is also why there's a really good chance if you jumped off a high bridge into water, it's not going to be like jumping off a diving board. So you're like, the water doesn't want to get out of the way. Yeah.
So if you broke the surface tension, you would die.
There's a good chance you'd reduce your injury. So, how do you break surface tension if you're like, I'm falling to my death on accident? Yeah, you throw soap down. So if you have anything you can throw ahead of you to basically create a little bit of agitation, that'll reduce your injury.
Rocks before they jump off cliffs?
I'll get to that. If you happen to have some Dawn dishwashing liquid, that would be the best thing. You're like, ooh, I have Dawn. So that will reduce the surface tension a little bit. But Mythbusters found that the actual amount of damage that you'll experience if you throw like stuff down and break the surface tension ahead of time, it's about the same. You're still probably gonna die. But that's okay. The impact won't kill you. What will kill you is you're going to be paralyzed, and then you'll sink to the bottom and you'll drown. So the impact won't kill you.
That would be the best one.
Yeah, that's going to be the best one. So if you're thinking about doing yourself off by jumping off a bridge, just realize that's how you're going to go. You're going to hit the water. It's going to crush a lot of your bones. You're going to be paralyzed.
But if you throw
then
a
you'll
gator,
drown.
But if you throw a gator, it'll be sick way to end it.
Right, like I said, the Mythbusters found that the actual amount of mitigated damage is very small. So anyway, but that's surface tension. On the other hand, if you want to do a belly flop into a swimming pool, spray some dishwashing liquid ahead of you, then you'll be okay. You'll poof right into the water.
Yeah, but that my pool has dishwasher, my next dishwasher.
That's true, but that could be interesting. That could be a lot of fun. Adhesion is the forces of attraction for different molecules. Water molecules stick to you because there is adhesion. Okay. The reason you get out of a swimming pool wet is because water has adhesive forces. Adhesion means sticky. So cohesion is a tendency to stick to similar molecules, water to water. Adhesion is the tendency to stick to other water molecules, water to you, or other molecules. Now, there's liquids that have almost zero adhesion. Liquid mercury has extremely high cohesion, but almost no adhesion at all. If you filled your swimming pool full of liquid mercury, first of all, you can't swim in it. If you tried to if you tried to jump into liquid mercury, it would go up to your shins. And then you'd just be like floating in liquid mercury, because it's super, super dense. But when you got out, there wouldn't be any mercury on your feet. You're like, hey, there's no mercury on my feet, because mercury doesn't have adhesion. Yeah.
So why is everyone like
Because mercury vapor will go into your brain and stay there forever.
Your body can't flush it out.
Yeah. Mercury vapor will go, it'll get into your body.
You shouldn't swim in.
No, you couldn't swim in mercury. Because basically mercury will go into your body, it will condense into the liquid, and it will stay wherever it is. Okay, ladies and gentlemen, copy this diagram down and make it big, because we're going to be writing a lot of stuff on top of it. So this is the phase type change diagram. It's in textbooks, it's all over the internet, it's everywhere. So you have gases here, solids here, liquids here. And then each of these arrows is a phase change. The phase change from a gas to a liquid is called condensation. The phase change from a liquid to a gas is called evaporation. The change from a solid to a liquid is melting. The change from a liquid to a solid is freezing. And then a couple words you might not have heard before you did your crossword. The change from a solid right to a gas is called sublimation. And the change from a gas to a solid is called deposition. You probably don't have a lot of experience with sublimation and deposition, because we have atmospheric pressure, which keeps it from happening for most things. But think dry ice. Dry ice goes from a solid right to a gas. That's sublimation. So copy the diagram, make it big. It doesn't have to be Picasso, which doesn't have to be Renoir. It can be Picasso.
So abstract.
I put from a solid to a liquid.
Who looks like that? I do. Can I eat this one?
Greetings in
A gas to a solid. Solid to a gas.
All right. So looks like some of your diagrams are done.
Not yet.
Let me need another half a minute.
No, 45 seconds, please.
And then we're going to label this with, in each of these phase changes, which one wins? Is it the intermolecular forces, or is it the kinetic energy that wins the competition?
Kinetic energy. How do you draw a dinosaur?
You
Same thing.
make an S, then you make a more bigger S.
For a dinosaur?
No, for a trogdor.
How do you draw a cube?
A square, line, line, line.
What is a
Connect.
trogdor?
What's a trogdor? You guys just gone. You have to Google what's a trogdor.
Alright, I'm gonna.
Not now. When you're in your English class, you can Google what's a trogdor. Okay, so let's start with the simple ones. The phase change from a solid to a liquid is melting. When melting occurs, which of the two, kinetic energy or intermolecular forces, is winning? The kinetic energy. When a solid melts to a liquid, the kinetic energy is larger than the intermolecular force. In other words, the kinetic energy is now overwhelming the intermolecular forces. And it should make sense that the opposite's also true for freezing. When a liquid freezes to a solid, the intermolecular forces are now overwhelming the kinetic energy. Now when a solid sublimates right to a gas, think dry ice you put on the anthill to kill the anthill. When a solid sublimates right to a gas, which one's winning? The intermolecular forces or the kinetic energy? Kinetic energy. For sublimation, the kinetic energy is overwhelming the intermolecular forces. And it should make sense when a gas is depositing to a solid, it is the intermolecular forces that are larger than the kinetic energy. And then go ahead and do condensation and evaporation on your own.
Okay.
Condensation is what happens when a gas condenses to little water droplets, and evaporation is what happens when you sweat and it evaporates, cooling you down.
Oh, I see how you did it. So all the ones in the middle.
I didn't design it that way, but yeah. This is a diagram from your textbook, and it's replicated multiple times all over the internet in every textbook. Every now and then your textbook has something good in it. So, evaporation. For evaporation, which one wins? Yeah. So evaporation is the kinetic energy that's overwhelming the intermolecular forces. And for condensation, it is the intermolecular forces that are overwhelming the kinetic energy. Okay? You see how this works? Now, we've talked about these phase changes. What's new for this unit is the idea that these phase changes can happen at the same time. This water, there is some of the water molecules that are evaporating. Some of the water molecules are recondensing. It's happening at the same time. And when multiple phases or multiple phase changes happen at the same time, what we call it is dynamic equilibrium. Dynamic meaning movement or powerful or energetic, and equilibrium meaning multiple things happening at the same time. So, in a dynamic equilibrium, two phase changes are happening at the same time. There's boiling and condensing, there's freezing and melting, there's deposition and sublimation happening at the same time. Equilibrium is a huge concept, not just in chemistry, in biology, in physics, in economics, in sociology. You guys remember that movie with Russell Crowe, A Beautiful Mind, where he goes crazy and he sees numbers and codes and newspapers? Have you seen that Beautiful Mind with Russell Crowe? Anybody?
No.
Just a few of us? Okay, so just the cool kids have seen it. If you haven't seen it, you should see it. So the basic thing is, John Nash is, he basically comes up with, he goes crazy. He's got a mental disorder. But before he does that, he has this idea of economic equilibrium. And he won the Nobel Prize in economics for it. He was a mathematician that won the Nobel Prize in economics because he came up with this crazy idea about how markets would work together. Markets work in equilibrium. Let me show you what I mean. Let's say you're going to open a really simple hot dog stand. And you got hot dogs. And when you sell hot dogs will give you money, right? Okay. When you sell the hot dogs. But if you can't sell the hot dogs because you got a lot of hot dogs, will you have a lot of money? No. If you sell a lot of hot dogs, you'll have very few hot dogs, but you'll have a lot of money, right?
Yeah.
Or you're going to have way too many hot dogs and very little money. Make sense? Well, here's the problem. If you sell all your hot dogs, you'll have money, then you can't make any more money. Or if you don't sell your hot dogs, you will not have any money. So what you need to do is you need to find a balance of your hot dog price where you sell a lot of them and make a lot of money. Okay? You want to balance out how many hot dogs you make and how much money you get. For instance, if you're like, my hot dog's going to be 50 cents. In an hour, they're all gone. You haven't made very much money. My hot dogs are going to be $10. You're not going to sell any hot dogs. So you got to find just the right price. And this idea is economic equilibrium. It's the basis for supply and demand. If you're one of the losers who wears Supreme, you don't understand supply and demand.
What do you mean, dude? That's like the brand.
Just a brand, man. It's the urban wear. But Supreme understands supply and demand. They keep the supply very, very small, driving up demand so they can charge hundreds of dollars for a baseball cap.
Hey.
Nintendo understands this too. When the Wii came out, they released very few Wiis, drove up demand, so they basically could sell a lot of them really inexpensively. Chemistry does the same thing. If you have a whole bunch of one type of thing, a whole bunch of reactants, so let's just replace this with reactants and products. If you have